now need to process this data so as to achieve your objectives. The first objective was to determine the distribution of metal concentration around the coastal Anglesey, so the distribution of metal concentration with distance. The first thing to do then is to work out the average metal concentration in the replicates, and to do that just use the average. We have missing data for site 7 because the fucus vesiculosus was not present. However, a different type of seaweed was present, Ascophyllum nodosum, and the concentrations for Ascophyllum nodosum are given here. Because we're controlling variability by using only one species of seaweed, we can't just use the Ascophyllum nodosum metal concentrations. However, we did collect both types of seaweed at site 8. We collected Ascophyllum nodosum and Fucus vesiculosus. So one way of approaching the problem is to compare the two different seaweeds collected at the same site and find a correction factor. It's not a perfect solution, but it will allow us to fill the gap, and as long as we are explicit in our methods to explain that's what we've done, then it's an acceptable thing to do. So we have the mean for the Ascophyllum nodosum and the mean for the Fucus vesiculosus, and if we divide the mean for the Fucus vesiculosus by the mean for the Ascophyllum nodosum, we get a correction factor by which we can multiply the Ascophyllum nodosum data in order to make it comparable to Fucus vesiculosus. So we can enter the Ascophyllum nodosum data from site 7, but multiplied by the correction factor, and the correction factor we just need to make an absolute reference to it. So we now have a full set of average metal concentrations in seaweed for each of the sites. So we now need to consider the variability within the replicates, which is our uncontrolled variability, and we're going to quantify that using the standard deviation. Standard deviation, we're just going to choose to use standard deviation. Remember not to use standard deviation P. As these are only 10 of what could be an infinite number of measurements. To turn our standard deviation into a confidence limit, we need to first of all convert it into standard error. So we take the standard deviation and divide it by the square root of the number in the sample. The number in the sample is 10, so 10 to the power of 0.5, that's the square root of it. So in that bracket we have the standard error. The standard error needs to be multiplied by the t value. The t value we can put in here is going to be T inverse. We're working at 95% confidence, so 0.05. The degrees of freedom is the number in the sample minus 1, so that's 10 minus 1, which is 9. So we have our t value, and so we can take our confidence limit by multiplying the standard error by the t value, and just make sure we have an absolute reference to the t value so we can copy it down. And there we have our confidence limits. Now we need to use this data to achieve our objectives. So our first objective was to determine what the metal distribution was with distance around the coast of Anglesey, and the best way to show that would be to draw a graph with distance on the x-axis and concentration on the y-axis. So to do that, we highlight the independent variable, which is distance in this case, and then highlight the dependent variable by holding down Control. And then insert a graph, and we should choose a scatter plot because that has a meaningful x-axis and a meaningful y-axis. We don't need a title because we're going to write a legend under it when we put it into our report. We do need to add axis titles, horizontal axis title, the distance, kilometers, and the vertical axis title, the concentration in milligrams per gram. Now, most important for this exercise, that we also need to add error bars. We've worked out our confidence limits. We need to transfer these onto the graph. To do that, we again select the graph, go to design, and then add chart elements, one of which is error bars. We don't want to use any of these that have been pre-calculated because we've already worked out our confidence limits, which is what we want to transfer on. So we can select more error bar options, and again, we don't want percentage or standard deviation or standard error. We want to choose custom, and then we can specify the value, and you can click on there and then highlight the positive error bar, and then the negative, which of course are the same number as it's plus or minus this confidence limit, and then we can click OK, and it draws the error bars on for us. Excel has a habit of drawing error bars in both the X and the Y direction. We don't have X error bars because we haven't got any errors recorded in our measurements of distance. Most likely there are errors, but we've decided they're not significant and we've left them off. So the best way to deal with the ones that are automatically put on there is just to highlight them and press delete. And then we're just left with the error bars or confidence limits on the metal concentrations. We can only actually see one of them, and that's probably because the others are so small, but we can check that by rescaling. instead of letting the axis run up to 800 milligrams a gram, if we leave it to go only to 50, then allows us to see at higher resolution the lower concentrations. One of the things that you need to consider is, do we need to be able to see the error bars on the small numbers? Is that relevant? The choice is not trivial, but it's answered, as always, by considering what's the objective. What are we trying to do? What is our objective? We're trying to show the distribution of metal around the coast of Anglesey. Do we need to see the error bars on the low concentrations in order to do that? You need to give that some thought to decide whether you can show a single graph or whether you think you need to show two graphs, one at a scale up to 800 milligrams a gram and one at a scale up to 50 milligrams a gram. The second objective should also be achieved ideally by the same figure. Your second objective was to show whether the metal concentrations, not only what their relative distribution was, but how do their absolute values compare to metal concentrations at other sites that have been judged to be contaminated or lightly contaminated or uncontaminated. That can be done on the same figure if the metal concentrations from those sites is transferred onto the figure. The data are available to you in the Word document. The comparison sites are a site that's very heavily contaminated by metal mine drainage, very similar to the Afon Gogh, and that's Restronget Creek, through to the Mersey estuary, which receives diffuse inputs of metal from all the various sewage treatment works, industries that are within the Mersey Basin, which is where Manchester is. And the Mersey discharges into the Irish Sea, and the Irish Sea is mentioned in the justification for doing this work. So the metal concentration in the Mersey estuary then is a valuable comparator to the data that you've collected. So we should transfer the metal concentration of Restronget Creek as the highest and the metal concentration of the Mersey estuary onto your figure. And this can be done by labelling a column for Restronget Creek and a column for the Mersey, and then putting in the metal concentration for each. And then adding these to the graph. Select the data and then add. So added those data points, and then we've changed them from being points to being lines. So we wanted to plot our data as points. There was no need to connect them. It would be misleading to connect them. It implies that we know what the concentration is between the points, but the standard values for Estronget Creek and the Mersey Estuary, we'd like to draw them on as lines because we want to be able to compare those values to all of our data points. Now that we've got more than one data set on the graph, we need to add a legend. So again, if we go to add chart element, we can add a legend, and maybe put it at the bottom. There may be a few other things that you could do with that to improve the appearance. That does a reasonable job of dealing with your objectives, and that's what we'd like from your figures. The figure should really be associated with an objective. Ideally, in this case, it's associated with both objectives, which means it's more concise and the reader can spend less time having to look at the data because it's presented in such a way.